let's make a simple assumption, reasonable, simple assumption. Assume all keys are natural numbers. What are natural numbers? 0, 1, 2, 3. Integers. Do not include negative integers. In the real world applications, actually, we need to handle negative keys. It's possible to have negative key values. It's okay, yeah. But here, for non-negative integers, we can easily convert to natural numbers. Okay, so there are many ways we can handle it. So don't worry. So, yeah. But in our discussion, the idea is the most important. So we just want to get an idea. Okay, all right. There are M slots. Yeah, so we consider this abstract data structure. It has M slots. So we need to arrange the data in those M slots. Yeah. All right. The question, how to map a relatively large key to one of the slots? So this question, this is our main question we discussed in the B.1. Yeah. The answer is hash function, right? So the question, how to design that hash function. Remember the 3 criteria. The first one, the calculation must be fast. We don't want to waste time in calculation. So the calculation should be extremely fast. Okay? All right. So the first method, very simple method, given like this. H of k, the hash value, hash function value. So the key given, you enter the key into the function, the output is this value. Modular operation, mod m. Right? M slots. So mod m. Okay? Yeah. That's the simplest hash function. Okay? Very simple, fast, right? We can evaluate it extremely fast. Easy to calculate. Right? Another question, we need to check other criteria, right? Evenly distributed, not quite. That cannot be guaranteed. Okay? It depends on the keys. Sometimes evenly distributed, sometimes not. So for this probably there is a question mark. Not not very satisfied. Yeah. Caught by any pattern? Yes, we need to study. So is there any pattern? So for this method, if there is a special pattern in our data, when we apply this hash function on those keys, do we map most of them in a relatively small number of slots? That could happen. So later, we will see some example. Yeah. All right. So let's see how to make hash functions robust. Yeah. All right. I want to use one simple example to show you what mapping function is not very good. Okay? Yeah. The first example, let's consider m equals 15. So we map our keys into 15 slots. Okay? So we have this function. Yeah. All right. So now you can see, suppose there is a pattern in the data. So what pattern? When key is a multiple of 3. Yeah. Suppose all our keys have this property, multiple of 3. Okay, yeah, this special pattern. Then you can see the hash function value h of k is also a multiple of 3 because mod 15. After mod 15, also multiple of 3. Okay, why is that? Because the difference of the hash function and the original key should be 15 multiple of certain integer number n. Why is that? Because look at this operation, division method. This hash function value basically is a remainder when you do division. K divided by 15, the remainder is your hash function value. So now the remainder and original number, take the difference, that should be 15 times some integer n. Okay, so with this property, then you write your hash function in this way, 15n minus k. Remember, based on our assumption, k is multiple of 3. 15n minus multiple of 3, the whole number is multiple of 3. Right? So that means among those 15 slots, only the slot numbers that are multiple of 3 excuse me, could be used to store the data. That's 1/3 of the data. Okay? So multiple 3, 1/3 of the data. Okay? That's not efficient. So you have 15 slots, but you can only use 5 slots to store your data. So that's a really bad algorithm. Okay? Yeah. So that's the reason this method, not robust, very bad, caught by the pattern, certain pattern. Yeah. All right. Another example. All right. Example 2, this time we consider n power of 2. 2 to the nth power. So this time your hash function is like this. Okay? Yeah. Now look at another pattern we may have. If 2 keys have the same last R bits, this is the pattern. Okay? Some of the keys have the same last R bits. Okay? So yeah. If for that special pattern, then those keys will be mapped to the same slot. Same slot based on this hash function, same slot. Then it's not efficient. Although we can handle that, but the efficiency will greatly reduced. Yeah. All right. A good choice of division method. Now we want to look at this. Yeah. So we try to avoid the problem we saw in the previous 2 examples. We try to avoid 2 problems we observed in those 2 examples. So the method is we use a prime number. M is a prime number, right? Prime number. The 15 is not prime. 15 equals 3 times 5. So that's why when the data has the pattern multiple of 3, the prime number, so we don't have that. The prime number cannot be written as a product of 2 smaller integers, positive integers. So we use that property. That is not too close to any power of 2. No. So that will break the second pattern. Yeah. Not very close to power of 2. Okay, so this property will break the second pattern. Yeah. All right. Then If we can choose this kind of m and do the division method, then our hash function will be much more robust. Okay, yeah, but relatively better. Yeah, still, we cannot guarantee, it is ideal. Still, it may not be that ideal. Okay, yeah, and then this method is empirical. Doing experiments. Yeah, can check. Pretty good. Yeah, but it cannot be proved. Yeah. All right. And even that, it is possible to create a special pattern to make it perform poorly. So no matter what number you choose for m, okay, so you can choose a number, okay, but some carefully, specially designed pattern in your data could make it perform really poor. That's possible. Yeah. But even that could happen, the probability is very small. That could happen, but the probability for that situation is extremely small. Okay? So we can accept it. So we can accept that. Yeah. The worst case, very bad, but if the probability is extremely small, so we can take it. Yeah. All right. So that's part B.2. Okay.